Good morning, everyone. We are just about to start our program. Our honorary speaker has already joined. So I request Mr. Rawashi Chakraborty to start our program, and also request Shubhasi sir to make our honorable speaker co-host. Over to you, Rawashi sir.
Very good morning to all of you. Today is the fourth day of our faculty development program organized by Civil Engineering and Mechanical Engineering Department of Greater Kolkata College of Engineering and Management under JS Group. This FDB is on advanced material and their characterization. Today we have very special and eminent speaker, Professor Dr. Robibroto Mukherjee sir. Professor Robibroto Mukherjee sir is from Chemical Engineering Department from IIT Kharagpur, and he is the charge of the atomic force microscope installed at the Central Research Facility at IIT Kharagpur. Without much delay, Professor Robibroto sir is also with us. So I will request our speaker, Professor Robibroto sir, to start the session. Sir, can you hear me, sir?
Yeah, so am I audible to everyone?
Yes, sir. Yes, sir.
Okay. So
you can start,
now,
sir.
Yeah, let me now share my screen.
Yes, sir.
So thank you, everyone. All the management of Gkcem, particularly the principal, whom I know for a long time, and all the organizers, the faculty coordinators, and all the participants. Of course, it's a pleasure to be here. I would have been happier to be physically present and give a lecture, but it's fine. It saves a lot of time because I'm in Kharagpur, so traveling often takes a lot of time. So let me share. I'm not very comfortable in Zoom, but let's see, I think it will work. So I guess all of you can see my screen, right?
Yes, sir.
Okay, thank you. So, yeah. Right. So I'm going to talk today on a very special type of microscope, which is known as the atomic force microscope. However, it is a very important tool today, present-day tool, though to be very honest, it is not as popular as the scanning electron microscope or the transmission electron microscope may be, but it is nonetheless a very, very important tool for material characterization. And it is actually not an overstatement that the tremendous progress in the field of nanotechnology, which we started to have from early 90s, is in many ways related to the development of the atomic force microscope, which actually is a rather new instrument because it was invented only as late as 1986. So let's see. You can see the whole screen, right? Or you are seeing the panel bar on the left or whatever?
Yes, sir, in full screen.
Okay, fine. So here, what you see is a microscope image of some zinc oxide nanoware, templated growth of zinc oxide nanoware. This is something, some research I do, so apparently it may look quite beautiful. So you see that you have these nanowares only at certain locations, which are sort of surrounding some voids, which are all ordered in an hexagonal matter. So this is a very, very nice scanning electron microscope image. You can see the scale bar that is here. So you can see that the nanowares or whatever, these are very nicely faceted. These are hexagonal in cross section, and roughly each side is about 100 nanometer or of that order, right? So there's another example I can give. So this is the example of line grating patterns you can see. And if you compare the two images on the left side and on the right side, of course, you see that the scale bars are actually different. So this one is 15 micron, this one is 20 micron. But if I ask you whether the images are of the same system or not, the answer will probably be, yeah, they look to be at the same system, but at different resolution or different magnification. And I would like to make this talk, though it is online, as interactive as possible, because we have been doing a lot of online teaching. And I know that many people during the online presentation just turn it on and do this and that. But I can guarantee that about 1 hour, 15 minutes, if you listen to what I'm going to tell, you will at least have some idea about what is the atomic force microscope, right? So I'd like to again request all of you to have a detailed look at this scanning electron micrograph and see if there is any information that is missing or anything that is missing in this particular slide. And apparently, most people who are doing some research in material science, right, you will feel, no, this image looks to be pretty nice, so you can claim a lot of things here and there. But the ground reality is, you are, so what are actually you seeing? You are seeing a photograph, right? So basically, there is not much difference between this photograph or a photograph you are going to take with your cell phone camera, in the sense that any photograph, what you are doing is you are mapping a 3D space into a 2D plane, right? So a printed photograph or a sheet of paper or on your screen. And this always comes at a price of something, and the price you actually pay is the information about the height is actually missed in any microscopic image. So some people actually do some tilting of the scanning electron microscope stage and try to gain some height information, but take it from me, scientifically that is wrong, because when you are tilting, the beam actually impinges on the sample at a particular angle, and the scale bar that you are seeing is actually for the projection, and there is actually a mismatch. So we get some sort of a information about the topography or height by tilting the stage in a scanning electron microscope, but you actually miss out on the real information. Those of you who are well aware about the confocal microscope, I will towards the end, I will also try to differentiate and give you an idea how confocal microscope actually offers far poorer resolution as compared to an atomic force microscope in the height or the vertical direction. So coming back to these two pictures, the reality is they are different. Why they are different? Because what you see now, and actually what you are seeing, is an atomic force microscope or atomic force microscope images of these two samples. You can see that topographically they are similar because they are both line grating or optical gratings, you can say, or gratings, but their heights are different. And that their height is different is something that even your finest scanning electron microscope will fail to capture. And for that, what you have to rely on is an atomic force microscope. Some of you might argue that, well, you can have a surface profilometer, and you can also get this type of information. But the ground reality is the surface profilometer, the vertical resolution is much poorer. So if the difference in the height or the heights are of the order of few tens of micron, then a surface profilometer will work. But if the heights are of the order of few nanometer, the profilometer is not going to give you anything. I mean, the profilometer will show it is like a flat surface. So let us try to understand what exactly is this atomic force microscope. And it turns out that in early 1990s, 1980s, the scanning probe microscope was first produced for real space imaging of surfaces. If the organizers allow, I can share this presentation with all of you so you can have an idea about it. Don't read too much about what is written here. So I have to fill up a slide, so I have just written something. So basically, the scanning probe microscope is a tool that sort of allows you to scan or get an information about a surface and its 3D topography. This is the most important thing. I know what I am saying is not making sense to most of you right now, but it's a guarantee that within about 20 minutes, it will start making sense. So a little bit of history about the atomic force microscope, and it is very exciting. And after listening to this history, and as practicing scientists, engineers are nothing but scientists because engineering is nothing but application of physics. So you will be quite happy to find out that you have learned about such an instrument. So the predecessor, so AFM was discovered in 1986. Unlike, let's say, the scanning electron microscope, which was discovered in 1950s, or optical microscope, which is much, much earlier. So basically, there are two people, Gerd Binning and Roher. These were the two persons. You can see their photograph. They discovered the atomic force microscope in 1986. But interestingly, the predecessor to the atomic force microscope was something called the scanning tunneling microscope, or the STM, as they call it. And this was discovered in 1982. And interestingly, the STM was so powerful that this duo was awarded the Nobel Prize for their discovery in 1986. So from the fundamental discovery to the Nobel Prize, the STM still holds the record for the shortest duration. Only in 4 years, the Nobel Prize was given. And look at the motivation of these scientists. We will understand why they did actually. That while on one hand, for their pioneering discovery of the scanning tunneling microscope in 1982, they were getting the Nobel Prize in 1986, right? Same year, they were circumventing some of the problems they realized after the discovery of the STM and led to the improvement of the instrument in the form of discovery of the atomic force microscope in 1986. Ideally, in my opinion, and in the opinion of many, many other people, they should have been given another Nobel Prize for their discovery of AFM. And the ground reality is today, the atomic force microscope, the popularity and the sales of the atomic force microscope is far, far higher than that of the scanning tunneling microscope. The way we will the way I will unfold the story today is first, we will have a quick idea about the STM so that you understand what the STM does. Now, STM involves tunneling, or the phenomena of tunneling, and which I really, I'm not a physicist, so I really do not know about tunneling that well. And I also understand that this workshop is being organized by the Civil and Mechanical Engineering Department. So most people might be having a background in one of the mechanical engineering sciences, or engineering with mechanical sciences background, pretty much like me. You may not be great exponents of physics. So we will try to understand what is tunneling current in the very simple form. And from there, we will realize what is the limitation of a scanning tunneling microscope and how the improvement led to the atomic force microscope. So basically, this is another slide. So basically, what the generic class of the instrument is called the SPM, the scanning probe microscope. You, at this point of time, to be very honest, you don't even understand why it is called so. But I will try to revisit this slide towards the end. By that time, you will understand very well why it is called a scanning probe microscope. And there are different microscopes under this category, but what we are going to learn is very initially a little bit about the scanning tunneling microscope, and then we will put our effort in understanding the basic operating principle of the atomic force microscope. And the way I am going to talk is, I come from chemical engineering, so I learned atomic force microscope while doing my research. So I have a sort of a more of an operator's perspective. So I know exactly how the instrument works. And if you really want to become an expert of an instrument, knowing the software or how to load the sample is one part of the story, but you really can extract the maximum from an instrument if you also understand the underlying physics. Therefore, understanding an instrument inside out is not the easiest thing. And if you really take that pain, you actually understand at least what exactly is going on. And another thing I see very often these days is that many times people are using an instrument for a sample. They have no idea why it is being used, what exactly to expect out of it, and something that is coming out, people are very happy that, okay, I have one more scan or spectra or an image, and they just attach it. That doesn't really work. So the whole idea that I have, though I know time is very short, because I teach a course in IIT Kharagpur in which I teach atomic force microscope over about 5 lectures. That's about 7 hours. But I think 1 hour you will still have a reasonable idea about how the atomic force microscope works. So moving on, basically, this is the fundamental concept of a scanning tunneling microscope. So we all know about electrical conduction, that if there is an electrical wire, you have a conductor and you apply a bias or a voltage at the two ends of the wire, so electric current flows. This we all know, and from our school days, we also know about resistance and Ohm's law, etc. But what is STM? STM is very interesting, or the phenomena of tunneling. So it's like if you have a very sharp metallic tip, so please do not forget it has to be a metallic tip. Sorry, I forgot to bring my tab, so I'll use your mouse. And if you bring it to another metallic surface, and then what you do is then if you sort of apply a voltage across it, right? So then what happens is there is flow of current. So this is what is known as tunneling current. And this separation distance is of the order of few nanometers. So you have to have a really sharp tip. That tip has to be very close to a metallic surface. And then you apply a voltage across the tip and the surface. And if the tip is very, very close to the metallic surface, there is going to be electrons passing from the tip to the surface. So this is the phenomena of electrical tunneling, right? This is a quantum mechanical phenomena. Let's not get into the details. But please do understand the other thing that is very, very important, that the strength of the tunneling current is a function of the tip surface separation distance. So if the tip is very far away, then of course there is going to be no current. But if the tip is close by, and then if the separation distance is lower, right, the strength of the tunneling current would increase. Of course, one of the limiting cases of the tip movement is if the tip goes and touches the surface, then the tunneling will stop and there will be a short circuit, because the electrons will start to flow due to electrical conductivity, right? And there will be no tunneling. And on the other hand, if you take away the tip from the surface, of course, eventually the strength of the tunneling current will drop. So in a nutshell, what we are going to discuss is the strength of the tunneling current is a function of the tip surface separation distance. I hope this is clear to all of you. The other thing is, when we are saying that there is flow of current, we all understand essentially means that there is flow of electrons. And in a conductor, these electrons flow through the material or the conductor itself. And we all know from a material standpoint that the free electrons in the outer orbitals, right? They actually are the one who participate in this kind of motion, etc., etc. These are basic, simple, very, very basic, simple physics. So let's not get into that. But here, what you need to understand and really feel excited is where are the electrons passing through? The electrons are passing through the air or the gap that is in between the tip and the surface, right? So yes, it is a fact that the electrons are passing through this gap. So if it is the atmosphere is ambient, like there is air all around, what is going to happen? These electrons, which are now passing through air, would basically collide with the molecules, air molecules, right, which is oxygen and nitrogen mostly. And consequently, the electrons will get scattered, and the signal that you will get, right, as a measure of this tunneling current is going to be very, very low. or may tend to 0. So basically, it's a good idea for the STM or the scanning tunneling microscope is to have very high vacuum so that there are no air molecules with which the electrons might collide and get scattered, right? So if you understand this much, so basically we now understand the concept of tunneling current. And if you understand this much, now let us see that here we have a surface, right? This is a surface, which has to be a metallic surface and a conducting surface, etc., etc. And now all of a sudden you see that this particular tip you now understand. So this is a tip, and you bring it very close to the surface, and then if you apply a voltage, here the tip surface separation distance is d1. So let's say you get a magnitude of tunneling current which is I1. Now you move the tip to another location, which let's say the surface is little higher out there. So basically what is going to happen? The tip surface separation distance is going to drop, right? And as the tip surface separation distance going to reduce, what is going to happen? You have a new tip surface separation distance. So let's say the strength of the current is I2. And I guess all of you who are listening to this talk, if you are following me, whatever I am saying, it is also easy for you to conclude that I2 is going to be higher than I1, right? So if that happens, what you can do is that, so basically in this way, what happens is that as you move from at every point, if you just move the tip at different locations, right? At every point, basically, you can find out the value of the tunneling current. You now know that how the tunneling current varies, right? As a function of the tip surface separation distance. So you can, at all the point, you can consider of a imaginary datum, and from that you can subtract the tip surface separation distance, and you can mathematically reconstruct the contour of the surface, right? So basically, from point to point, the variation in the magnitude of the tunneling current can be converted or translated to a line, right, which sort of has identical geometry as that of the cross section of the surface. I hope you understand it. So basically, what happens that once you do this calculation, so from the variation in the tip surface separation distance, you can sort of reconstruct the surface. So this is basically the idea about a scanning tunneling microscope. And what you basically learn is the constant height mode, right, of the scanning tunneling microscope or the STM. Why constant height? Because the tip moves at a constant height, right? So really, in an online session, I cannot check whether all the participants are able to follow. But I really hope that at least this much you have been able to understand. Sorry. Yeah. So with this knowledge, let us now just focus on, are there any limitations of this particular approach? And yes, of course, we understand that there is a limitation of this particular approach, and that is like you are going to move the tip at a specific height, right? So you have no idea that whether how rough the surface is going to be. And it is quite possible that at some point of time, if the surface topography instead of this, the topography is like this, right? Then what is going to happen? What is going to happen is when the tip is going to move like this, it's simply going to hit the surface at this location, and the tunneling will be lost. And the moment there is a conduction, of course, the magnitude of the current or the strength of the current will significantly improve. That will lead to short circuiting and damaging of it. So it has its limitation, we understand. So what is the alternative? Alternative is basically to just use a feedback loop along with this tip. So basically what you do, you take the tip at the first location, you measure the strength of the tunneling current, and then you move to the second location where also you measure the strength of the tunneling current, and you find out that, of course, the tunneling current is higher there. So feed this difference between the first and the second points to the tip. So there is this feedback loop. You feed the difference to the feedback loop so that the tip is what to do. Tip is moved upward at a new location so that the tunneling current becomes I1 again. And if you now track the movement of the bottom of the tip, so it becomes identical, or the tip moves exactly in phase along with the contours of the surface. So basically, I hope you all understand this. Of course, it's a schematic.
Excuse me, sir.
Yes, please.
Actually, sir, PPT is not visible right now.
Is it? Just 1 second, please. So this I have been told a long time back. Thanks for pointing out, really. Is it visible now?
Yes, sir. Yes,
Oh,
sir.
this you should have pointed out. I'm really sorry. I don't know what exactly happened. So should I repeat something? Everybody could see?
Yes, sir.
Okay. So I'll just repeat this part. So basically, the improvement that was suggested was that you have a feedback loop, feedback mechanism along with the tip, so that from point 1 to point 2, if you move on, so there is an increase in the tunneling current, and you just feed the difference, right? This difference between I1 to I2, you feed to the feedback loop, and the feedback, the controller sort of responds in such a way that the STM tip moves upward, and you get back the same value of the tunneling current. And this way, you can sort of modulate the movement of the tip in such a way that it sort of follows the contours of the substrate. So as if it's behaving like a tracing paper. And so what you have learned is now is basically the constant current mode of the scanning tunneling microscope, STM. And what is the advantage? So unlike the constant current, constant height mode, right, where there was a possibility that the tip might collide with the surface, that possibility is ruled out here, right? So this actually works pretty well, and I'll show you later that this information, if you just make the tip move up and down over a 2D area, you actually get a 3D information with a little bit of image processing. But I hope this is clear to you. Really, I cannot check it in an online class whether everybody is on board. But what I can say that, what I should ask at this point of time, that do you still feel that agreeing to the fact that the constant current mode is a significant improvement over the constant height mode, do you still feel that there is some limitation? And the answer to this is more than you and me. Thank God that the inventors themselves realized. So this work was published in Physical Review Letters in 1982. And such was the strength of the discovery that they were given, as I told, the Nobel Prize in 1986. But the inventors could immediately identify that such a powerful technique, which is able to sort of give the true 3D information about a surface with nanoscale resolution, is actually limited only to a metallic or a conducting surface. And large number of different type of material like polymer, ceramics, semiconductors, right, insulators, this technique could not be extended for analyzing the surface topography of such surface. And what was the problem? The problem was that you need to have some indicator or some parameter which the variation of which can be directly related, right? Can be directly related to this variation or the topography, can be related to how the topography is changing, right? So I guess all of you understand here that in an STM, what is being utilized is the basically tip surface separation distance, and how the tip surface separation distance modulates the variation in the tunneling current. But unfortunately, now I guess you will all understand that if the bottom surface is not conducting, even if you bring a tip, bias it, apply a voltage, there is going to be no tunneling current. So you really cannot measure this difference. So how to circumvent this problem? So basically the whole, so I guess you understand all this now, what is written here, the constant current mode, constant height mode, etc., etc. So basically, moving on, we now understand. I mean, I will follow the presentation, but we will sort of try to understand it logically. So basically, the whole idea that emerges is the concept of atomic force microscope. So if you want to do a similar measurement or some sort of a similar approach for a non-conducting surface or for any surface for that matter, what do you need? You actually need an analog that is going to replace, right, the tunneling current, because tunneling current is specific only to conducting surfaces, right? So what can be done? Oh, the easiest thing to do is to basically, so what we need to understand that while tunneling current is specific to conducting surfaces, there is something that is always active between two molecules or two surfaces, and that is the intermolecular interaction, or what is known as the van der Waals forces. Now, we all know about van der Waals forces, but some of us might not immediately recall what it is. So it is basically the sort of interaction between adjacent molecules and neighboring molecules because of the localization of the electron cloud. Basically, it is the most general form of van der Waals force, which is known as the dispersion forces or the induced dipole force. So what exactly is that? It is basically if you just go back to the concept of Rutherford atom, that where you have a nucleus at the center and the electrons are encircling it, etc., etc. Something we have again studied in our school days. The reality is you have a very nice picture of electrons evenly distributed, and then you have studied somewhere how they are similar to the solar system and different from the solar system. Reality is these electrons are undergoing a very high frequency rotation around the nucleus. So at any given instance of time, there is actually a localization of this electron cloud around the nucleus. So like this. And what happens? So this localized electron cloud, which leads to some sort of localization of delta minus, induces a positive charge in the neighboring atom or the molecule, right? So now, since you have a delta minus over here and a delta plus over here, there is now an attraction. But this attraction is transient because of the fact that next moment, the localization of the charge might be somewhere else, and it might induce something else. So this is the most fundamental, or the induced dipole interaction forces. It scales as 1 by r to the power 6, where r is the intermolecular separation distance, the nucleus to nucleus separation distance. And if you just plot look into the force versus distance curve, it looks something like this. So if the separation distance is large, the interaction force is actually 0, because you can just put some large value of r over here, and then you can see that the force tends to 0. But if you bring it closer, as the separation distance, so this is basically r. So as the intermolecular separation distance starts to reduce, the strength of the van der Waals force starts to increase till a point where basically the two approaching molecules start and touch each other. Now, what exactly is touching? Where the outer orbitals sort of interact with each other. And that leads to, of course, you have electron in the outer orbital of both the molecules. So that leads to a very strong electrostatic repulsion, which is like this, and which is known as the bond repulsion. And I guess some of you, or most of you, might have been aware of this particular potential curve, which is known as the LJ potential, or the Lennard-Jones potential, right? So this induced dipole interaction is universal. So the whole idea was that if we now replace, if you want to have a technique that is valid for any type of surface, so the whole idea was you replace the tunneling current with something that is universal, and that is van der Waals force. So the whole thing that you are going to do, you still use a tip like this. Why you use a tip, we will understand it later. So basically, this is the tip, and you bring it close to any surface. Now, unlike an STM, you don't even have to bias to see the flow of electrons or tunneling current. But if the tip surface separation distance is less, there is going to be a non-zero van der Waals interaction between these two surfaces, right? I think this part is clear. And now, conceptually, of course, this is not exactly how an atomic force microscope moves. So if the tip now moves from this point to this point, the intersurface separation distance is going to increase, and therefore the strength of the van der Waals interaction is going to reduce. I hope this is clear to all of you. So you can see from here that if R increases, right, the strength of the van der Waals interaction actually reduces, provided, I mean, before it completely moves to zero if the separation distance is very high. So this is the whole idea. And why the word atomic force? The word atomic force is used because these microscopes operates based on the principle of interatomic interaction or force between atoms, right? So this is the genesis of why the name atomic force microscope is used. Now, all this is fine, but there is only one problem. And the problem is, I don't know how many of you can guess what is that problem. The problem is that when you are working with tunneling current, you could directly use a picoammeter to measure the current. And therefore, if you could measure the current, you could immediately find out what is going to be the difference in the current as it moves from point 1 to point. But how do you measure van der Waals force? Turns out that there are no direct techniques which are available to measure the van der Waals force directly between two surfaces. So a slightly complicated or not complicated, an indirect method is used by which we cannot, though we cannot measure the exact magnitude of the van der Waals force, the intersurface force, but we can still find out their variation as it moves from point 1 to point 2. And remember, in this constant current mode, we have had a feedback loop. So if you can feed to this feedback loop what is the variation from point to point, that itself is going to be enough to modulate this intertip or the tip surface separation distance, and you are going to get an idea about the topography of the surface. So let's see what are the components of a AFM. And in about 20 minutes, you will realize that suddenly you are understanding everything. So you see, this is the sample. This we already know that we are going to have a sample. Again, as I already told, there is again a tip. But unlike an STM tip, where you had a really sharp metallic tip to trigger tunneling current between the tip and the surface, the tip in an atomic force microscope is slightly different. In fact, it is mounted on a cantilever, on a small cantilever or a micro cantilever. It is mounted, right? So this symbol subsequently you will see, or this notation you will see in many of the presentations. And in fact, you can see it already here. So this is the cantilever I am talking about, right? This is the cantilever I am talking about. And here we have the tip. And then there are two additional systems that we have. There is one is a laser source, and the other one is a photodiode, right? So one is a laser source, and other one is a photodiode. Now, these three collectively are collectively used. So this laser source, this photodiode, and this tip are collectively used to track, as I mentioned, the variation of the force between tip and surfaces, right? So this is what is going to be, and we are going to understand and learn this part of how it works nicely. In fact, this is the crux of understanding an atomic force microscope, and once you understand this, you suddenly realize it's a very, very elegant technique, and next time onwards, if you ever sit in front of an atomic force microscope, you exactly know what is happening. And then additionally, there is one more thing that we need to understand, that we say the piezoelectric scanner. It is basically to which, I mean, this piezoelectric scanner is also there for the STM, but deliberately I did not talk about it. So this tip is basically mounted to a scanner. So we will learn about that. You can also see this is the ACM image of an atomic force microscope probe. So you can see that this is the actual how it looks like. And so schematically, we are going to represent it like this. So all modern instruments come with a computer interfacing, that is obvious. And again, taking a clue from our understanding of STM, you also see that there is a feedback loop over here. So I guess this apparently complicated figure, you will slowly get clearer and clearer to all of you. So let us see what is written here. So probes or tips, we already understand. We are going to learn about the photodetector, the piezo. We understand that there is a feedback loop. And there are certain things, particularly these two operational aspects, which I am going to make you understand. Each one will take not more than 5 minutes each, which will give you an even better understanding, right, about the instrument, how it works. And then a little bit of how this data that we collect, how it can be converted to nice looking microscopic images, because ultimately we are all human beings and we are trained, though we do a lot of spectroscopy, a lot of graph, XRD, this, that. Ultimately, we are all very happy to see something, because seeing is believing. Just give me a minute, please. Okay. So moving on, we are first going to focus on this part of the instrument. So basically, we are going to understand, right, the role of this laser diode, the laser source, the tip, and the quadrant photodiode or the photodetector first. So this will also make us understand the process of alignment. And then we are doing all these things to understand the morphology or the topography of the sample. So for that, we will understand what is approach. And please feel free to keep your questions or remarks noted. So I'll be very happy to answer some of them once I'm done with my presentation. So here is the photodiode. In fact, it's a very special type. So what is a photodiode? Even if you are not a physicist or do not come from the ECE background, it is very easy to understand. So it's a photodiode. Photo means if you shine light on this diode, electricity will get generated. So it will show some readings. But this is a very special type of a photodiode. In fact, it's called a quadrant photodiode, right? So basically, you have a circular diode like this, and you actually see these two. And if you see these two axes like this, what is the first thing that comes to your mind? The first thing, we are all engineers or scientists, that comes to our mind is a Cartesian graph paper. And that's exactly the case. So quadrant means that if you consider this to be a graph, there are going to be 4 quadrants, first, second, third, and fourth. And this photodiode is is designed in such a way that if light falls at the center, the reading is 0. If the light falls, so as you move from the center to the periphery, right? Just one second, please. As you move on from the center to the periphery, just one second. Center to the periphery, the strength of the current increases. So generally, in the most of the commercial photodiodes that are used in atomic force microscope, the variation is from 0 to about 10 millivolt, right? So any concentric circle, right, sort of is like, so you will have a concentric circle from 1 millivolt, 2 millivolt, something like that. And any point, basically this diode, so let's say these 2 points lie on a concentric circle, right? So basically what we know that maybe their reading for both of them is going to be 4 millivolt, but this photodiode can sort of independently tell you the X and Y coordinates. So they can distinguish between the 2 points, right? So this is basically the idea of the photodiode, quadrant photodiode. And what I'm completely skipping is how they are fabricated, because that's a million dollar industry. This is all very complicated microfabrication process, but let us take for granted that these instruments are available, or this hardware is available. So as you can find out, the general range is 0 to 10 millivolts, the center being 0 millivolt. Of course, if there is no light shining on this photodiode, then there is no reading. Okay. So now you see that we have basically 3 different components, and let us try to understand what is this process of alignment. And individually, you see that what you understand. So we have a photodiode. We now understand the quadrant photodiode that we have. And we also understand that if laser light falls at the center, the reading is going to be 0 millivolt. We have this, here is the tip, as I already mentioned. So we have the tip, and the tip is mounted to a cantilever. You can see this is the cantilever. And then one more detail, let me just highlight at this point of time, is that so you basically have a cantilever like this, to which the tip is attached, and the area that is exactly opposite to the tip on the cantilever surface, right? So you have some sort of a micro mirror out here. So it's sort of a mirror. Only this part of the cantilever is shining. Okay. And also what you have a laser source. So laser light is coming, right? And if you recall, these are the components we are talking about. You see, here is a laser source, here is the cantilever, here is the quadrant photodiode. Now you see, so this cantilever has basically 2 screws. You have 2 screws which you can rotate. The photodiode also comes with 2 screws which you can rotate. And what you are going to do, you are basically going to do, so you have a reflective coating. And now what you do, you first turn these 2 screws in such a way that the cantilever comes in the path of the laser light. So as you sort of move it appropriately, and in the older instruments, we used to do this step of alignment manually. That actually gave us an excellent control over the alignment process and how the system was configured before the scanning starts. So now as you move the screw, so what happens? Eventually, your objective is that this reflecting surface comes in the path of the laser light. And what is going to be the consequence? If a light beam is falling and you bring in a mirror, it's going to reflect, right? I hope this is clear. Earlier, so before it was brought in, basically the laser light was going straight away like this. And now after you have brought it in, it starts to reflect, right? Your next objective is now you turn the 2 screws associated to the photodiode, right? And you rotate it in such a way that the photodiode is brought in the path of the reflected laser. And eventually your objective is that the light falls at the center, and you know what is going to be the consequence. The reading is 0 millivolt, right? So now what you have learned in the process is what is known as the process of alignment, right? So what exactly that is? That is basically optical coupling between the laser source, the tip or the cantilever, and the photodiode. So now you see the tip is perfectly, or the instrument is perfectly aligned, right? So great. So this is one good step. But what is the next thing that you need to understand? That you have done all these alignment, etc., etc. You understand that, okay, there is a tip, there is a photodiode, everything. But all you have done is to get information about the surface. And as of now, the surface is nowhere in the picture. That is true. In fact, this whole process of alignment is done far away from the surface. Why do you do it far away from the surface? So that you do not want that when you do things with your hand, there's a lot of vibration and shaking of your hand. That should not destroy that. So please understand that the sample surface is, this is the sample, and this is pretty much far away. And sample for an atomic force microscope has to be solid, so no powders or liquid can be scanned. generally a thin film or any surface, and there is absolutely no sample preparation required. I don't know if you had a talk on scanning electron microscope or microscopy, or even if you had a talk whether all these minor details was highlighted to you. Like for charge neutralization in a scanning electron microscope, you actually need to have, so for non-metallic surfaces, you need to have some sort of a metallic, sputtered metallic coating. But for an atomic force microscope, no sample preparation is required. Only thing is it has to be small. I mean, theoretically, you can scan the surface of a brick, but you will not be able to mount it. But a small piece or a film is perfectly well. But up to the stage when the alignment is done, the tip is far away from the sample, right? Okay, so now what needs to be done? So as it is far away from the sample, we now understand based on, I mean, everything, every single point you should understand. So if the tip is far away from the sample, let's say somewhere over here, the intersurface van der Waals force is 0. So it does not really solve any of your problem because you cannot measure anything. So what is the next thing that needs to be done? Next thing that needs to be done is you need to bring the tip close to yourself. And that is exactly what we are going to do. And as it is written here. So that process of engaging the tip along with the sample or to the sample is known as the process of approach. Now, before I move on to approach, I would like to highlight what we have not mentioned so far, that this cantilever is actually mounted to a piezo scanner, right? It is mounted to a piezo scanner. But so what is a piezoelectric material? Piezoelectric material in very simple terms is if it's a such type of a material that if you apply a force across the material, current will get generated. So if you compress it or if you elongate it, you will get some current, positive or negative. Or if you apply a voltage across the material, it will shrink in its size. In fact, it is the second property that we will utilize in that in the operation of an atomic force. Now, what to do? But this approach process, what you are going to do is a very simple thing. That is, you are going to physically bring the sample close to the cantilever, right? So between frames 1 and frames 2, if you compare, you see that the sample was far away, and now you are bringing. How do you do it? You do not do it with the help of the piezo scanner. You have a separate motor or a stepper motor for that, which sort of brings the sample. Either you can bring the sample close to the cantilever, or you can bring the whole cantilever assembly, which of course has to move along with the laser source and the quadrant photodiode close to the sample. Either is fine. So it depends on, it varies also from manufacturer to manufacturer. Most common, of course, is bring the sample plate close to the cantilever, right? So it is coming. So between locations 1 and 2, both the locations are quite far away from the sample. So there is going to be no variation in the strength. So what I would like you to request, I'd like you to look into is very carefully that I guess this configuration, everybody now understands that you have a laser source. This is the reflecting part of the tip, and the light is falling at the photodetector at its center. I would also like you to simultaneously draw your attention to the LJ potential curve over here, and also look into the configuration of the tip over here. So as it moves, there is though the separation distance has reduced from 1 to 2, there is actually no variation. So there is no variation here. So the reflected laser light continues to fall at the center. Now what happens? You have brought the tip, you brought the sample even closer to your tip. And now what is the consequence? So let's say point 3 is somewhere over here, right? There's a little bit of got distorted. Point 3 is somewhere over here. And so now what is the nature of the interaction between the tip and the sample surface? The nature of the interaction is attractive, right? So here comes the importance of the choice of the cantilever. What type of material you should take for the cantilever? You should take a cantilever which are all microfabricated, which are sensitive to the type of the magnitude of the van der Waals forces that experiences or that is active between the tip and the surface. Now the strength of this force is very weak. So if you take a steel cut rod or danda, which is very, very rigid, right? It experiences a minor force, but it does not deform. It doesn't serve your purpose. So you should take the cantilever that is malleable enough to deform to the strength of the forces that is active between the tip and the surface. And I hope that everybody now understands, as you bring the sample slowly close to the tip, there is a reduced, there is an enhanced interaction between the tip and the surface. And as a consequence, the cantilever sort of deforms. But don't forget that this cantilever that is deforming is already optically coupled to the laser source and the quadrant photodiode. So there is an immediate consequence of this deformation. And what is that? The laser light, which was falling at the center, now does not fall at the center. It falls at somewhere else. And it is falling over a photodiode. So immediately what you can also note is that there is now a variation in the reading. Earlier at all these locations, the reading was 0 millivolt, right? But here it is no longer going to be 0 millivolt, it's going to be something. And what we observe, or the way the orientation is done, that the reflected light falls in the third quadrant. Okay. Now, what you do, you don't stop here actually. You continue this approach, right? There are two questions. So once it experiences the intersurface attraction, should we stop? The answer is no, we do not stop. We continue, and as a consequence, what is going to happen? What is going to happen is the obvious thing. There is no rocket science, and therefore I will encourage all of you to start thinking, because now you are in a position where you know major part of the atomic force microscope. So eventually what will continue is that the tip and the surface will come in contact like this. And despite or even after coming in contact, if you continue this pushing up this sample, then what is going to happen? Now this tip is no longer behaving like a cantilever, it becomes like a pivot. And basically, if you continue to make the sample move upward, sorry for the horrible sketch, if you keep on moving it upward, then basically you are now traversing this part, right, of the force curve. And what is this point? This point when the tip surface contact has been established. And as you now keep on pushing it, what is going to happen? The nature of the deformation or the deflection of the cantilever also changes. So earlier it had a concave deflection, then slowly the extent of deflection reduces, right? It eventually starts like this. Eventually it becomes straight again, no deflection, like when it was far away from the sample. When does that thing happen? That thing happens when basically the strength of the attractive interaction and the repulsive interaction are same. So basically the force curve intersects this line. So here also the net force is 0. Here also the net force is 0. Here the net force is 0 because there was no interaction, right? But here the net force is 0 because the attractive interaction and the repulsive interaction, the strength of the attractive and the repulsive interaction is same. And if you continue to push the tip beyond, of course, if you continue pushing it, what is going to happen? The tip is going to break. That is the final thing. So you do not do like that, but you go all the way up to somewhere over here, right? Where the configuration of the tip is something like this, right? And then you stop. The question to ask is, when does this upward movement stop? You see, in this schematic, there was something which I did not explain, right? And human mind, so if I don't explain, nobody will also ask. There was a green spot. This green spot is what is known as the set point. This set point is set on the quadrant photodiode. Let's say I choose that the set point will be 3 millivolt or 4 millivolt or whatever. It is sort of an operator prerogative, but it also depends on the type of the material you are going to use. So stronger is the material higher set point you can use, but for softer materials, we generally use a lower value of the set point. So when the deflection sort of matches that of the set point, the upward movement stops. I hope this is clear. This is not the easiest concept, and often in a talk about an introduction of an instrument, we do not look into these minute things, and therefore things become actually very boring if you just see some downloaded images from different papers. This guy has done this AFM and that AFM. I mean, I do not like to talk about an instrument in that. So here the upward motion stops, and this is when we say that approach has been achieved. So please do understand that though conceptually we talked about the inter-surface separation distance to be utilized for the atomic force microscope, right? In reality, to achieve better resolution, we actually do not operate in the non-contact regime, but we actually operate in the repulsive regime, where the tip is firmly pushing against the surface, and consequently, there is a deflection in the cantilever, right? So now that this configuration is achieved, so over here, what happens? What happens is very simple. So the upward movement of the sample stops, and basically this says that the approach is complete. And completion of approach is also associated with this piezo, right? We talked about this piezoelectric scanner over here. Piezo now getting activated. So up to this point, the piezo was not active. So at this point, the piezo gets active. Okay. I hope this is clear to most of you. Something is written, I will try to share. So this picture now, if you look, you suddenly understand. So this is actually a subset of this schematic we started, and I told you roughly 20 minutes you will start understanding. So some strange schematic which we often see here and there and never care to understand what actually is there, you suddenly see that the major part of the picture is now clear to you. Why? Because you see that you have this tip, the cantilever end, you have this tip, you have this shiny mirror type thing. It is mounted to a piezo, right? You have a laser source somewhere, and you basically have this you can omit. This should not be scanner. This is actually the scanner. You have the sample, right? And you have a feedback loop, which we haven't talked about yet. And where the light is falling, it is falling at the set point. So let me just ask you, what do you think is going to be the unit of this set point? This unit of the set point in this particular case of an atomic force microscope is in terms of millivolt, because in reality, from the hardware standpoint, you are setting the set point on the photodiode. So the reading is in millivolt. So now this is the piezoelectric scanner. So basically one uses a hollow circular scanner. I mean, I think I will skip this detail. So now again, if you see all these figures, you will understand each one of it. And now what we need to do, basically what we are going to do, that you choose a zone of interest, right? So let's say we pick up a 5 micron by 5 micron area or something. And what my tip is going to do, so the tip is going to sort of do a raster. So it moves on from one point to the other point as a line. Then it comes back, moves to the next line, goes back, goes all the way, then comes back, then moves all the way, comes back. So basically this movement of the tip is sort of basically a nested do loop. So first it keeps on moving along this line for a particular value of, let's say, y equal to 0, for different values of x equal to 1 to, let's say, n. Then it comes back from x equal to n to 1, then moves to y equal to 1, and so on and so forth. So this is this direction of x. It is called the fast scan direction. This is called the slow scan direction. And these are interchangeable, in fact, for any atomic force microscope. So instead of rastering like this, the tip can also raster like this. That's not an issue at all. So now what happens during rastering? So let's say this is my point 1. Of course, don't get carried away. These are all very exaggerated views so that you understand. So let's say that on any surface, the tip has approached here. And these are very practical considerations. So nowhere we are considering that the tip is either going to land on the highest point or the lowest point. No guarantee that it's landing on Mount Everest or Mariana Crater. It can start from any point. Now let's say from point 1 to point 2. So let's say this is the sample. So this is like point 1. This is our point 2. And what I have done is I have exaggerated, right? So point 2, as you can see, is at a higher elevation, right? So as the tip moves from point 1 to point 2, what is going to happen? Here, the point is at a higher elevation. So the extent of compression in the tip is going to increase. I hope this is clear to everyone, because the tip is already compressed like this. Now, if it moves to a second point, right, which is closer, the extent of compression is going to increase. I hope this is clear. And the moment the extent of compression or the deflection is going to change, what is going to be the consequence? The consequence is the reflected light, which was earlier falling at this point, now falls at some other point, right? So the moment it falls at some other point, and this is our set point, right? So now there is a difference, right, between the voltage value, between the point where it is now falling and where the set point is. And it is all about a feedback loop. Everybody understands the moment we have an error or a deviation, you can simply feed that error to the deviation to the feedback loop. And what will the feedback loop do? That feedback loop will actually feed this voltage across the piezoelectric scanner. And consequently, the piezo will change its size in such a way. In this particular case, the piezo will become fat and short and wide, so that the bottom of the cantilever to where it was mounted can actually go up, so that the extent of compression reduces. And what happens? The deflection is again back to the initial level, right? So here and here, the extent of deflection are same. So this is exactly from as it moves from point 1 to point 2, from every point to its subsequent point. So first it moves to the next point, then it checks whether the deflection has changed. If the surface is atomically moved, then there will be no vertical displacement. But otherwise, from point 1 to point 2, because of the topography, the deflection will change. And accordingly, whatever is the consequent deviation on the quadrant photodiode, that information will be fed to the piezo, and piezo will move up and down accordingly. So basically what you do, that after, I think the spelling is wrong here, I think it will be raster RUS. So after you have moved from point 1 to point 2, so basically for every point at the end of the scan, so after the tip has moved from this point to this point after doing all the rastering, you basically you don't have a picture in an atomic force microscope. Unlike a microscope or a cell phone picture, what you have is a data set like this. So for every point, what is the variation in the Z as compared to the first point where it started, right? So now what you do, you basically find out the range of this Z, you normalize the values between 0 and 1, and use some image processing software to generate a grayscale, and you artificially get an image like this. Right? It looks like a beautiful image, right? And you have certain zones which are dark, which are certain zones which are bright. And you need to look into the vertical scale bar. So don't forget, so just don't get carried away, wow, this looks such a nice image. And from our understanding, we can immediately see that here there are some trenches, for example, right? And here there are some stripes and here are some features. But not only that, you look into the color contrast. So here the darkest zone is 0 and the brightest zone is 140 nanometer. So please do understand that in an AFM, you are not seeing a true image, but this is all a rendered image. So all color or whatever is artificial. This is like artificial color. And do not try to sort of gauge the difference in the color from there, try to get, okay, this looks like 1 micron, nothing like that. So whenever you are using an atomic force microscope image, not only the lateral scale bar is important, but also use the vertical scale. This is where the additional information that you will get, right? So this is what is it? So normalize with respect to the total range, and then just create a contrast, and you have an atomic force microscope image. And AFM image, the colors are always artificial. And also, please remember that whenever you are using an atomic force microscope image, you must add the vertical scale bar, because even in top journals, I have seen people are using an atomic force microscope image without a vertical scale bar. So they don't even know how much information they are missing. Okay, so this is what we learned, and this is also my style of teaching or telling things. I never declare what we are going to do because I do not believe in names. What we have learned is the contact mode of atomic force microscope. Why it is contact mode? Because from point 1 to point 2, the tip is always in contact, right? And then you judge what is the difference in the error. So this is beautiful because it now works for any surface. You do not require any conducting surface, or there is no specific requirement. But there's still some limitation. And what is that limitation? A contact mode is like drawing a pencil along the paper. And we all know that if we use a lead pencil for a long time, what is going to happen? The tip is going to turn blunt. That is one possibility, right? The other possibility is that if you press the pencil very hard on the paper, you might actually, you can pierce through the paper. So exactly the same thing might happen. So firstly, in contact mode, though you get very good resolution, right? The ground reality is that the tips, because of friction and abrasion, the tips deteriorate very fast. This is number one. And number two is you need to understand that instead of a very rigid sample, if you have a soft sample, then the contact mode is extremely detrimental, and it may actually cause some scratch on the side. So what is the alternative? And the alternative is what is known as the tapping mode or the intermittent contact mode. And that is another brilliant invention. And it takes advantage of the fact that a cantilever basically acts as a spring, right? So this also acts as a spring. And what is done in this tapping mode or intermittent contact mode? In fact, I do not want you to use the word tapping mode because it's actually the technology of one specific manufacturer, and intermittent contact mode is scientifically more valid terminology. So what you do is you have an additional drive motor which adds to a frequency or which oscillates the tip. Now the question to ask is that at what frequency you oscillate? You basically oscillate at the natural frequency or the resonant frequency of the cantilever. So every instrument, the option is there that you find out, you can do a tuning and you can find out what is the resonant frequency. Because what is the why you use the resonant frequency? You have to give minimum power from outside to get the maximum amplitude. So what you start doing now is instead of working with a static cantilever, you now have the same arrangement, same piezo, same alignment, etc., but you start oscillating the cantilever. And what is the extent of oscillation is your choice. And what is the consequence of the oscillation? It's interesting. So here is the quadrant photodiode, and earlier you had a stationary tip. So the light upon alignment was falling at 0, 0, but now the tip is oscillating. So you do not have the laser light falling at a specific location, but even on the quadrant photodiode, you see that it is oscillating, right? So these are something is there, but don't get into too much details, but try to sort of understand the basics of it. So the whole idea is that now, this is actually how an AFM looks like. This is from my own lab. So this is the instrument, but again, don't get carried away. What you see over here is an optical microscope, and the atomic force microscope is only this much. Rest all is paraphernalia. This is a vibration isolation table. Only this part is the atomic force microscope. It's really very small. This part is the atomic force microscope. These are different manufacturers, right? But this often you have an atomic force microscope under an optical microscope to ensure this alignment process or help you in alignment process and things like that, right? So these are the things. So what I need to just tell, I will just wrap up now. So what you do is that while this is oscillating, now you approach the sample, and as you approach the sample, now because of the proximity of this sample, the oscillation will also get truncated, right? And now you can track with the help of this quadrant photodiode. So as the oscillation gets truncated, the magnitude of the oscillation also changes on the quadrant photodiode. And that difference you can feed to the feedback controller and let your piezo move, the scanner move up and down exactly in the same way what we have discussed. So what is the advantage? Advantage is you are not dragging the tip over the sample surface like before. And as a consequence, there is no scratching or direct damage to the sample. And also the abrasion is far less. So I think these are the two most important modes of atomic force microscope. There are a lot of additional things that you can also do with an AFM, but maybe in one lecture I should not cram so much information. So that is all what I wanted to talk. But before I end, since it's a beautiful microscope, so I just want all of you to enjoy some high resolution, really high quality atomic force microscope images of some samples. These are some are from my own group, some are from the centralized atomic force microscope that is there for IIT Kharagpur users as well as users outside the institute. And most of the images I am going to show are biological or soft samples, which are otherwise quite difficult to scan. So these are some fibers forming some mesh. So not only you can see them, but now as quite knowledgeable people, you also know that this height of this fiber mesh is about 4 micron, right? So these are some patterns on some biocompatible, bioactive silk fiber and membranes. This is the atomic force microscope image of a red rose petal, right? This red rose petal is very interesting because it's sort of, so this is the topography of a yellow rose petal. One of my students was studying. So these are very interesting. This is the structure. So rose petal exhibits what is known as sticky hydrophobicity. So if you put a drop of water there and turn the rose upside down, the water drop is not going to move. So it's sticky surface. These are known as what are known as sticky surfaces. So these are the topography that is there. Why the surfaces are sticky, how they are related to these structures, maybe some other time. But what you see is something very interesting. These are hierarchical structures because what you see that you have some micro domes, right? But the dome surfaces are not smooth. They are also decorated with some nanoscale features. And to be very honest, people often looked into biological entities with a microscope, right? And in an optical microscope, you will see these microdomes, no problem, but you will completely miss out on these nanoscale features that are present on the surface. These are a clustered colony of micrococcus bacteria, I think, some spherical bacteria under a microscope. And let me tell you, these are since bacteria, and these are very, very soft material. So it is very difficult to get such high quality, high resolution images. This is actually some kind of a cancer cell, in fact, on a cover slip. So you can, what you are seeing is the cytoplasm part of it. And again, what you are seeing here is just go back to your school days. If you, I know most of you are engineers like me. So this is actually the nucleus of some cells, what you can see. And this is some cytoplasm and some nucleus, how it is expanding. So some cell images under an atomic force. And yeah, some other images. So probably some adipose tissue or whatever, God knows what it means. I do not know. So I think I'll come to an end with that. Advantages of AFM, of course, it's now you understand it's a microscope, but it does not capture a photograph, right? So it gathers information in a completely different way, so that you sort of get a proper 3D topography with a resolution as low as about a nanometer. Also, like you do not need any sample preparation. It is totally generic. It works for all type of surfaces, right? And the other thing which we did not emphasize today, was first lecture, you should not go too much into the detail. I want, instead of just listening to something is going on, after this lecture, you have some idea about this atomic force microscope, right? So I think the other thing that you need to understand is that since the tip is going and touching the surface, right, you can actually do with that tip a lot of additional measurements, like you can do the frictional characteristic, adhesion, viscoelasticity, hardness, etc., magnetic domains, etc. And yeah, I think these are the salient last words I will have. So while you see in other microscopes, you actually touch a sample in an AFM, right? And the simplest and the biggest difference is you get a direct information about the topography. And of course, we did not talk about this part in today's lecture, but you do not only get to look, but you can also do a lot of stuff. So I think I will stop here, and thank you very much for your attention.
Thank you very much, sir. It was throughout a very nice and good session. Thank you for it. And now it is open to for all the participants. If you have any query, you can ask our honorable speaker any question. Participants, if you have any question, you can ask our honorable speaker.
I think nobody will have questions because people don't ask questions generally, but it's perfectly fine.
Yeah. So thank you, sir. So we are concluding our session here, but before concluding, there is a small token of love from our college, Greater Kolkata College of Engineering and Management for you, sir. We are sharing a digital memento for you. Kindly accept it.
Sir, hello, sir, but I cannot share the memento. Can you please look into it? I cannot share from. I think I'm
Please,
not co-host. That is why.
Wait for madam. So this is for you. Kindly accept it.
That is really appreciated. And at my end, I have taken a screenshot of it as a token of my acceptance. Thank you very much.
Sure, sir.
So I'd like to leave the meeting now.
Yes, sir. Okay. Thank you very much, sir.
Thank you.
So participants, we have already shared the assignment link and feedback link in the chat. So you just complete it, go through the link right now. And after that, they just break and the next session will be started from 3:45 p.m. So thank you, everyone.
So thank you. I'm leaving. None.
Very good evening and good afternoon to all of you. Once again, we are back with the second part of our FDP, the fourth day of this FDP, Advanced Materials and their Characterization, organized by Civil Engineering and Mechanical Engineering Department of Gkcem under JS Group College. Now we have another very eminent speaker, Professor Dr. Dipankar Mondal sir. He has received his PhD in 2008 from BTU Cottbus, currently known as BTU Cottbus, Senfenberg, Germany. Prior to that, he obtained his MTech in Materials, Science and Engineering in 2004 and MSc in Physics in 2002 from IIT Kharagpur, India and Jadavpur University. He works as a scientist, a professor at the Institute of Nanoscience and Technology, Mohali, India. He was an assistant professor in the Department of Physics, Jadavpur University, Kolkata. His research interests include the synthesis of advanced multifunctional materials, flexible electronics, piezo, tribo, pyro, and ferroelectric materials, organic photovoltaic and electrospinning system for the development of new generation nanofiber fabrication, 3D printing, smart textile, and non-invasive biosensor for healthcare monitoring, and designing mechanical and thermal energy harvester for self-power IoTs and MI-aided sensor. He has received several awards and recognition such as Young Career Award in Nanoscience and Technology in 2019 from DSP Government of India, Top Cited Author Award in 2019 and 20 from IOP Publishing, SBS Top 50% Highly Cited Authors in 2019-20 once again from India. His several findings are highlighted in editorial press release and from SCS and AIP, etc. Recently, he is enlisted as the 2% most influential scientist for 2023 in India as per the Stanford University survey. Currently, he is holding H index of 46 and his articles are cited 6,822 times. So we are very much grateful and thankful to sir that Professor Dr. Dipankar Mondal sir is here. Sir, I would like to request to start your session, please.
Okay.
Sir, can you hear me?
So,
Yes, sir.
yeah. So, you are also, I'm at audible also?
Yes, sir.
Okay, fine. So let me test few things like
Yes, sir.
I have to share the slide first and so screen share in this one. So now tell me the status. So it is okay now?
It's okay, not in full screen, sir. Yes, sir. Now full screen.
Full screen, okay.
Yes, sir.
And then how to get the laser pointer, because I am not much familiar, or is this our cursor is also
Yes, moving, sir.
moving? Okay.
Yes, sir.
So I can start now, right?
Yes, sir.
All right. So thank you very much. First of all, I would like to thank the convener and organizer for arranging this faculty development meeting, as well as for contacting me and giving the opportunity for delivering, some of my recent work and some fundamentals definitely. I also would like to thank Professor Muwadash because she asked me at the beginning, and so I agreed. So yeah, regardless of this, so I have designed my talk in such a way so that some of the recent work can be shared. At the same time, some basic are also, I try to cover some of the basic of the topic. So my talk is mainly related to the piezoelectric sensor. Okay, that is the main focus. So, and then I will mainly focus on the basic of the piezoelectrics and then some emerging applications. Okay, so this way I will actually move. And how much time I will get? So 45 minutes or 1
Yes,
hour?
sir. Yes, sir. You can get 1 hour. No issue,
Okay,
sir.
fine. All right. So let me start. So as we know, actually, even in the recent time as well, so we are very much, depending on the different types of sensors, right? And it will be even several fold order in next 20 years or so. So the main question is how we can make them sustainable. Because as we all know, some of the sensors are even, are kept in the extreme conditions. Some are in the underneath of the soil and water and so on. So they needs a sustainable power source, right? So this is one of the major concern. And then it became even more severe if we consider this particular sector, which is related to the healthcare. Okay, because if something happened with the power, then monitoring the patient is one of the major issue. And some cases even for even powering some other equipment, those are necessary for the monitoring the health. That is also important. So the summary of this thing is that like one need to provide the sustainable power for the all time. So and then I think we are very much familiar with this symbol, right? Because whenever we come out from the home, we always check whether we have a 10%, 20%, or 90% or not. Because this is not a luxury, but then it is a necessity nowadays because we want to, connect with the family, friends all the time, right? So you can imagine like if we, let's say, keep away our mobile phone for an hour, you may realize something is missing, right? So this is only because we are heavily depending on the this kind of portable gadget because it is not only nowadays mobile phone, it has a many other things that we can do actually at the same time. So this kind of handheld device, basically, we need a sustainable power source. There is no doubt about it, right? But then it became even more severe. Let's say if we do 1 hour for, let's say, sports, then we can avoid our mobile. We can keep our mobile somewhere else. But if somebody has a, let's say, pacemaker, then the power source which is required to run the pacemaker is very much important, right? We cannot keep, keep away for an hour so that something severe thing may happen, right? So that means we have to provide the sustainable power to the pacemaker in order to concern the other physiological things, right? So the questions comes nowadays, like even though the doctor said that lifetime achievement, so they always offer two package, whether you want a lifetime one or you want the little less one, less money. So the lifetime one, whenever we say, okay, we need lifetime one, but then it cost more. But then if you think a bit critically, that nothing is a lifetime warranty, particularly for the battery, because it has a certain lifetime, right? So, but they are very clever because they gave the morals at the same at that time. So that is very important on the spot, right? And it happened in the old age, particularly, kind of 70 or 65, so kind of generally it happened like that. So if you calculate like 5 years lifetime, then they calculate, okay, 70 plus 5 means almost, end of the lifetime. Or they are very clever. They said, okay, in every 2 months or so, you should visit us, and then we will check whether your other organs or things are going properly or not. So that time, definitely after 3 to 4 years, they will suggest it is better if you change it. Then the problem is like changing the pacemaker is much severe uh, than the cost of the pacemaker. Because it is in the everything is happened mostly in the old age. This is one of the problem. So people are thinking, how we can make them sustainable so that if you want implant inside the body, it can work for the forever. So this is the concept basically. So the concept of self power electronics came into the picture. What does it mean? That means like we want to run the electronics, particularly those needs a low power, or let's say those are portable, but we want to, we want to use it for the all the time without so-called charging with the additional, traditional charging like what we use nowadays. So they want to use some kind of feedback loop so that if we use the run them for the forever. So the concept of self-power electronics came into the picture. So for example, if we think about our, own energy sources, for example, blood flow, walking, finger tapping, etc. They also composed of the several sorts of mechanical energy, and that energy can be converted to some useful means like electrical energy. So self-power electronics can possible to run. Okay. For example, so this is the one of the schematic. So this shows that, for example, this lady riding the bicycle, and then somewhere here they have this kind of electrons. Okay. So it is composed of, let's say, some sensor. I'm not telling on what kind of sensor. Maybe it is piezoelectric, maybe it is something else, triboelectric, but they work in the very similar fashions. That means one has to apply the mechanical stimuli to them, and then it can convert to the electrical energy. So if we put some kind of like AC source to DC source, because vibration is always it has a positive and negative component, so we can charge our power source or different electronic gadgets. So you see, from multimeter to speedometer, hygrometer, etc., they have already been demonstrated. Okay, so this is the concept, like you have your own energy source and you are powering your own electronic gadgets. Okay. This is the self-power electron. So now, in order to in order to conceptualize the self-power electronics, the main idea is, one of the idea is using the piezoelectric materials. So now, if you think about the discovery of piezoelectricity, that was happening in 1880, so long back, So it is a mechanical energy to electrical energy conversion process. It's also work in reverse way too. That means if we apply the electrical energy, then it is the expansion and a kind of vibration is possible. So we can give a mechanical stimuli, and then we can able to convert to the electrical energy. This is called the direct piezoelectric effect. But if we apply the electrical energy in sinusoidal fashion, then we have a vibration, right? It's like a motor. And this one, the direct piezoelectric effect, was used as a energy harvester. That means the energy which is available around us, which is going to be wasted, like mechanical energy from the transportation, our walking, talking, etc. Lots of any kinds of vibration that basically, otherwise it get wasted. So that we can, if we use some materials, that is the piezoelectric materials, then it is possible to convert one form of energy, that is mechanical energy, to electrical energy, right? It also works in reverse way too. That means if we apply the electrical energy, let's say sinusoidal kind of frequency, if we use, then we have a mechanical energy kind of vibration. Okay, so that work for the motor. So one is the energy harvester, or let's say you can say generator, and if it is made with the nanomaterials, then it is called the nanogenerator. It's generating the energy. In other case, we are creating the vibration. Okay, so like transducers and some sort of motors, etc. Now, similar way, it also some of the piezoelectric materials also shows the pyroelectricity. That means they are also get excited if we apply the fluctuation of the temperature. So that means if we apply the thermal energy, then it is also possible to convert to the electrical energy. Okay, so thermal energy to electrical energy conversion process is very similar like thermoelectricity, but there is a difference with thermoelectricity and with the pyroelectricity. Pyroelectricity, they work with they need a temperature fluctuation, not a fixed temperature. For the example of the thermoelectricity, we need a fixed temperature gradient. That means hot junction and cold junction, something like that, and they have a fixed temperature. But in the case of pyroelectricity, one has to apply the change of temperature. That means with respect to the time, you have to give a temperature fluctuation. Okay, then it also work as a thermal energy harvester, or let's say generator, that can also able to convert thermal energy to electrical energy. It is also reversible phenomena. That means electrical energy to thermal energy conversion is also possible. That is known as electrocaloric effect. Okay. So many refrigeration work based on this principle, pyroelectricity. Now question comes, why this kind of phenomena is basically happening. Okay, what are the main reason behind it? So that I will discuss in a little bit detail, but then let me start with this way. So it is basically a crystallographic origin. So those crystals have a non-centrosymmetricity. So there is a space group in crystallography. They possess the piezoelectricity. So not like all materials give rise the piezoelectricity, no. the material need to have the non-centrosymmetry. One of the example is the zinc oxide, Rudgite class of zinc oxide nanorods. So let's say, for example, here you can see this particular crystals like zinc oxide. So if you apply the force F, okay, then there is a displacement of the ion, positive and negative, that give rise some sort of polarization. Okay, and this polarization, if we connect with the some circuit with the resistance, then there will be flow of electron. So we have a current here. Okay, so one of the classic example of there are many example in the piezoelectricity. Those are commercially available, many sensor, transducers, accelerometers, resonator, etc. But this is the example that we everyday we use. Okay, so you can imagine the commercial impact and the revenue they are earning from a simple gadget. That is the gas lighter. So in the kitchen, like everybody we use, so how it works. So if we give a force, and then there are two electrodes separated by a distance where the air molecules are there. So once you give a spark or heat to the crystals, piezoelectric crystals, there is a large electrical spark generation because of this air gap. And that spark is whenever it comes to the vicinity of the LPG, comes out as a fire. So that's the thing. But then you can imagine a small force of force of thumb produce a spark. So that needs a several kilovolt order of amplitude potential actually. So it is what I mean to say is that it is very powerful, because even if the small force can give rise this kind of potential. Okay. But then why people are so much excited about the piezoelectricity when it was discovered in 1880? It was discovered due to the Polish World War time, either first or second or in between, because there was a necessity to to send the signal from one side to another side. So is there in a hydrophone application was very much necessary that time. So it was discovered the piezoelectricity and for the commercial application. But in 2006, some miracle happened, means like then Professor J.L. Wang from USA, Georgia Tech, he has shown that if you make a zinc oxide nanorods like this, right side bottom figure, you can see the array of nanorods, and then actually his idea was to measure the Young modulus of a nanorod, which is not so easy. Like if you have a beam like aluminum beam in physics practical, we can calculate the Young modulus. Simply we have to put the load, we have to calculate the displacement. Okay, then we can calculate. But in the case of nanorod, it is not feasible, right? So what he did, he used a atomic force microscopy to estimate the Young modulus. So that was his idea. But then while doing the AFM, he has observed that once the platinum coated silicon tip is passing through the nanorod, he has shown that they have a different response. But once it is going to the top, so there is a bending of the the nanorod crystals, and it giving some sort of electrical spike. So you can see a lot of electrical spike from the surface, which is eventually when your tip is passing through the nanorods, it's giving the electrical signals. Okay, so that was the first discovery made by Professor J.L. Wang. So then this term is actually he coined, the nano generator. Okay. So this is a nanomaterials composed with the a nano generator composed with the nanomaterials. And then zinc oxide, we know it is also have a semiconducting property. So you can say the zinc oxide nanorods are semiconducting piezoelectric batteries. Okay, so this is called the nanoscale mechanical energy to electrical energy, because he shows that it is possible to harvest even, or let's say sense very tiny force like nano Newton type of force is possible to harvest. So this is the equivalent circuit diagram where like you can imagine like capacitance and resistance. This is a nano generator part, and it is connected with the external load. So it is a RL. This is the external load. So if you like go through you pass through our nanorod, so there is a signal that is a V0. So this is the maximum voltage. So we can calculate the lifetime. So this is the maximum voltage, and then it's decaying, right? So from the full width half maxima, we can tell this is the lifetime, 0.6 millisecond. And then from the RC circuit, we know the lifetime is R into C. Here R is the internal resistance from the nano generator, and this is the external resistance. So RL capital L plus R small. So if we make them equivalent to this time, then we find that the capacitance, of this nano generator is 1.2 picofarad. So this way we can able to calculate the capacitance of the nano generator. We can also able to calculate the internal resistance of the nano generator from the power curve. That I am not discussing, but the take-home message is that once we are making the piezoelectric device with the nanomaterials, then there is a very much efficacy to sense very tiny forces. So this is the take-home message in 2006 when the zinc oxide nanorod based nanogenerator came into the picture. So now then people start working on this particular area. It was opened up, and then in 2010 also the polymer community, they have also published an article from University of Berkeley Mechanical Engineering Department, Professor Chang's group. They have shown that if you make with the piezoelectric polymer nanofiber, then it is also possible to make the nanogenerator, which is even flexible in nature. Because zinc oxide nanorod, if we apply the much, let's say, mechanical force, then it may get get interrupt, and it will create the fracture. So long-term stability or workability is one of the problems with the zinc oxide nanorod. So you have to always restrict the force. But however, in the case of polymer, there is an advantage. You can apply as much force as we want. In the true sense, it is not the case, but then we can apply very extreme case, and they are very flexible because they are flexible in nature. So how they have prepared? They use, the kind of electrospinning process, near field electrospinning process. So which is nothing but a polymer solution they kept into a high, kind of syringe. So the doctor syringe, and then the doctor syringe consists of a needle, right? Like injection syringe. So that needle is metallic. That metallic needle and the collector. Again, collector is a metal. So they apply very high electric field between the needle and collector. And here they apply a kind of, syringe pump. So the polymer solution will pass, it will come as a droplet. But once you have a needle and you have a collector like this, so if you apply very high, the kind of pressure, then you will have a droplet, right? But if you apply electric field between this tip and collector, so after certain electric field, like 10 kilovolt or so, it depending on the manufacturers, but for the simplicity, let's say if we apply 10 kilovolt in the distance of 10 centimeter from the tip and collector, then you have a kind of fiber formation. There is a formation of the Taylor cone. You see the left side, this Taylor cone symbol, and then if we apply a critical voltage, you will get the fiber formation. So this fiber was collected, and this is the electrode. This part, right side and left side, you see these two parts are the electrode part, and the one fiber, the electric fiber, is there. Then what they did, they actually placed this fiber on the flexible substrate. So they have a two electrode apart is like 600 micron distance. They simply place a thread like a nanofiber. Okay, why it is called nanofiber? Because its diameter is lying within the range of the 100 nanometer, but then there is this length is like 600 micron or so. So this is the definition of the nanofiber. Okay, so now what they did, they gave a motion like stretching and releasing, stretching and releasing. So you can see, and then they measure the output voltage and current, open circuit voltage and short circuit current. And you see, once they give a motion like stretching, they have a voltage, positive voltage. And once they have released it, then they have a negative voltage. So this way it goes on. But then if one want to use this energy to, let's say, charge some capacitor or let's say any storage device, then one has to use the bridge circuit. So to make the negative component to the positive. Otherwise, that will get charged and discharge, charge and discharge. This okay. So this we all know. We need to make from AC to DC type of signal. But then the interesting thing is that if you look the current, it is very similar like voltage, right? The up and positive cycle and negative cycle, stretching and release motion. So you see the top right corner, current is dq dt, right? First order derivative. Now it is related, linearly related with the G33 Y, A, and epsilon 0, where D33 I will discuss later what is that. But the Y is the young modulus. Okay. A is the cross-sectional area and epsilon dot is the applied strain rate. That means if we increase the strain rate, then we can increase the current, right? Because it is linearly dependent. Definitely you have to consider about the, the some threshold value, otherwise it get interrupted and break. But then it is true that if we increase the strain rate, then we have a liberty to increase the output current as well, right? So similarly, if we increase, let's say if we made the materials, which is a higher Young modulus, okay, then also we can increase the current. And similarly, if the materials possess the highest piezoelectric or better piezoelectric coefficient, then again we can increase the output current. Okay. So piezoelectric coefficient is D33. It is nothing but it is indicating, it is basically a tensor quantity. So 33 indicating in which directions, maybe those who have a mechanical engineering background, they can understand better. But then for everyone, like this is nothing but the direction of polarization or direction of the, another is a force, another is the direction of the polarization. So that means you are applying to the z direction if your system is like this. And we are also measuring the current in the z direction, the same top and bottom. And then if we change like z direction force, and if we have, measure current x and y direction, then we can say 3-1, D31, something like that. Okay, so D33 is the nothing but is a piezoelectric coefficient, which is measured basically charge by force. So Q by F. Okay, this is the piezoelectric coefficient. Okay, per unit force, how much charge we are generating. That is the definition of piezoelectric coefficient. Okay, so now from right side this curve, we can see. So we know the energy conversion efficiency related to output energy by input energy, right? So in output energy V into I and dt, if we do the integration, because this is the time scale, okay, and input energy, which is the mechanical energy related with this formula, okay. So I am not discussing why it is came, because it's just nothing but a mechanics and geometry. But capital D is the diameter of the fiber. This is important. Young modulus Y, okay. So this is length. So now D, if the D is more, because it is denominator, you see, conversion efficiency. So if D is more, so definitely the energy efficiency will be. So you see, the fiber diameter is, if the fiber diameter is increasing, that means it is going to the more and more bulk regime, then the efficiency, energy conversion efficiency is decreasing, right? But if it is belonging to the little bit lower side, like nano diameter, then the efficiency is more. Similarly, if it a red triangle, if you see, this is the bulk, like film, okay, not fiber. The sensor made with the generator made with the film only. So you see the energy efficiency is much. Okay. So that means the take-home message is that, so if we make with the nanofiber, we have a better energy conversion efficiency. So if we reduce the diameter, then we can even able to improve the energy conversion. This is the kind of message. So like 2006, now we know that zinc oxide based nanogenerator came into the picture, and 2010 polymer based nanogenerator came into the picture. Then this field is basically is widened and getting widened, and then many other materials actually people start working, like cellulose, gelatin, many other chitin, many other polymers. Those have the piezoelectric property depending on their end application. So if you consider about the technological merit, it has several technological merits, because it is working in very it can cover two major sectors. One is the energy conversion, another is a sensing part. These two things. So it can be a very good sensor and it can be a very good generator as well, right? So now the question comes, how, and the sensor, how it can be used, right? So it can widen several area. For example, healthcare sector, it has it has a use as a heart rate detection, pulse detection. Then the giant analysis is also possible. How our we are moving our legs or giant, etc. Yeah, and there are also pressure monitoring system. Okay, with different types of pressure monitoring system. Somewhere in the brain, somewhere in the in the vocal cord. So kind of voice monitoring is also possible. Tactile perceptions, it is also possible. Blood pressure monitoring is also possible because they are related to the pressure change only. Okay. And now those are a little bit interested with the fundamentals. They can look on this particular triangle where you can see how they are coupled actually. So this is electric field, this is stress, and this is strain. Okay. So how they are interlinked, you can see the direct piezoelectric effect, there are electromechanical effect, direct piezoelectric effect, etc. Elasticity, how they are related. This is fundamental. I'm not touching, I'm just touching on this thing, not discussing too much detail. Okay. But then, as I told that the zinc oxide is a basically semiconducting piezoelectric material. But in the traditionally, those piezoelectric materials was discovered like 8080. There is no concept of the semiconducting property. So it is like very high band gap, like BaTiO3, PZT, lead zirconia titanate. So they are very high band gap. It's kind of dielectric, very good dielectric. Okay. But then if we able to couple this property together, like semiconducting property, photo excitation property, because semiconducting piezoelectric materials have a photo excitation property because they have a certain band gap. Okay. And then the piezoelectricity, then the fantastic area came into the picture, like some are like piezotronics, this overlapped area, some are piezophotonics, optoelectronics also came into the picture. That means if you have a like a sensor that can sense like the light, in a different frequency of the light, and that current, the once you have a piezoelectric, it is made with the piezoelectric materials, then the output, the current can be possible to modulate by the application of the string. Okay, that is called the piezophotonics. That means the piezoelectric current can be modulated also by the exposure of the light or vice versa. Okay, so that is another interesting area that I will not going to discuss in detail, but this is interesting. Okay. So now, for example, this one, you see they are applying the force and they are also exposing the laser light on the zinc oxide nano layer. So the current is possible to modulate. Okay. So as I told, so the energy has a different range, right? So depending on your end application, you have to design your device. Okay. For example, whenever I talk like I think 15 years or 10 years before, that time many people ask me these questions. Okay, your energy is very less, microwatt, milliwatt. What you will do? So now people also shows it is possible to increase to several, kilowatt range or watt range. At the same time, we have also seen and there are many handheld electronics where even lower power is also good enough to power. So in that case, you don't need to use, very lot of energy to, because anyway it is going to waste, or you have to scale down, you have to make it step down. So low power electronics is also came into the picture. It has an enormous importance because many handheld device made with the nanomaterials or microelectronics, it has been found that the low power, power requirements is not much. So in that case, this kind of device is possible to use. Okay. So you see, these are the proposed area where people have shown that it is possible to use like implementable medical devices, powering electronic, harvesting human energy, flexible electronics. It is also possible to make it hybridized so that the solar and piezoelectric both can be harvested, and many other earlier like some filter, also blue energy, another mechanical based energy harvesting in the large scale it is also coming because it is related with the ocean wave. So that's why it is known as blue energy. Similarly, electronic skin like robotics, because it can sense the temperature, it can sense the pressure, because temperature means it is pyroelectric. So because piezoelectric materials can also able to sense the pressure as well as the temperature. So it has a fantastic application as electronic skin. Okay. So and robotics. So can the it can cover its widen spectrum to as a end application. So this is all speculated things, but then few things are also in the marketplace. But then if we think about the fundamentals, then the question comes on the what are the materials, how we can choose that what materials should give rise this kind of emerging property. Then one has to consider this particular diagram where you can see the dielectric materials, in some of the dielectric materials are piezoelectric in nature, and some piezoelectric are pyroelectric, some are ferroelectric. So if you choose the ferroelectric materials, then that means it has a piezoelectric and pyroelectric properties too. But some of the piezoelectric materials like zinc oxide nanorod, they are not necessarily, they have the ferroelectric. So that's the material of the choice. But then the main origin of the piezoelectricity is the non-centrosymmetry. So one has to find out what is the space group in the crystals. So if it is found that they are non-centrosymmetric in nature, that means you can think, okay, it can show the piezoelectricity. Okay. So that's the first thing you have to consider. Then if you check this crystallinity like triclinic to cubic, so it is like ascending symmetry, but then out of these 32 point groups, like 21 class are non-centrosymmetric. That means quite large number of materials have the non-centrosymmetric, right? So those are like pure physicists. If the something symmetrical things get break, then many things happen. So this is the crystallographic symmetry is getting break. So this piezoelectricity, also ferroelectricity came into the picture. Okay. So ferroelectric materials means they have the spontaneous polarization, right? And if we apply the electric field, then that polarization is possible to reverse it. Okay. And then if you apply, if you consider the PE loop, ferroelectric loop, so there is a polarization axis, y-axis, and x-axis in the electric field. So if we apply the electric field, then there is saturation polarization. Then if we reverse it back, so if we decrease the electric field, then at certain, at zero electric field, you have some remanent polarization. So it also has the application as a memory, non-volatile memory. So as I told, the ferroelectric materials are very important because they also source piezoelectricity as well as the pyroelectricity. So you see lead zirconium titanate, PZT, so how it works. So in the case of, let's say, cubic system, they are symmetric at above Curie transition temperature. So there is a temperature known as the Curie temperature, so below which the ferroelectric materials work. So if you apply the above Curie temperature, then the ferroelectricity as well as the piezoelectricity will not work. So if you buy a device which is the piezoelectric, you can see the operating temperature regime dimension. Okay, you should work within the 100 degree, within 50 degree, 40 degree, something like that. So this Curie transition temperature determines the operating temperature of the device. So this is the temperature where ferroelectric to paraelectric transition takes place. And that means the dipoles, that is the origin of the ferroelectricity, they get randomized at this. So you will not get the ferroelectricity. So this is a cubic system, let's say, above TC. And then below TC, you see the non-centrosymmetry came into the picture. Okay. So this is give rise the polarization, positive and negative. This acts as a dipole. So this is one of the easy picture where you can see polarization is up, red dot is up. So you see the arrow, but then this is the down. So polarization is down. Okay. So this is the origin of the ferroelectricity. So in the case of polymer, maybe in the question you may find that which polymer materials are the piezo, ferro, pyroelectric. So this is the answer that PVDF is the one of the model polymer. Okay. Model polymer that can give rise the piezoelectricity. It is why? Because it is simple polymer. You see this linear polymer. So this is carbon main chain backbone, and one part is a hydrogen. So monomer unit like CH2 and CF2. So this is getting repeated. So now this H plus is basically hydrogen is a H plus. So this is electropositive, and this fluorine is very much negative. Okay, electronegative. This is electronegative. So this causes the polarization. All right. So this is the origin of the ferroelectricity because we need to have the dipole. So this is nothing but a dipole, positive charge and negative charge, and separated by a distance. Okay. This was I talking about. Like if you start from the zero electric field, x-axis is the electric field, y-axis is the polarization. So you see after certain electric field, you have a saturation polarization. So if you reverse it back, then you have a remanent polarization. Okay. So that means, these polymer materials, the ferrotic polymer, they have some memory. Even though you have a zero voltage or zero electric field, you have a certain memory, so it has the application as a non-volatile memory, flash memory, etc. So now one of the important phenomena or steps for the piezoelectric material. So once you choose a or prepare a synthetic piezoelectric materials, that means you are preparing them. Then one step is very much important, that is called electrical polling. So electrical polling, what does it mean? That means now we can think like this way: we have a system and we have several electric dipoles. So electric dipoles are nothing but the charge, okay, plus and minus charge separated by distance. This is one dipole, this is another one, this is another one, like that. So now if we apply the electric field, then what happens? They get aligned in a particular direction. So you see the positives are these directions and negative, the white part, are in another direction. Okay, so positive and negative, so this is called the polling state. Okay, this is called electrical polling. So you have to apply certain voltage or electric field so that all dipoles will get aligned. And then certain voltage, how? This is called the cohesive field. Okay, so you have to apply above cohesive field. So this particular state, you have a all dipoles will be aligned. Okay. So now if you reverse them, or if you make it zero, let's say if you switch off the electric field, then what happened? Your dipole will also not get randomized. You see, it is looking like a randomized because it is like this state, right? Initial state and final state will be very similar. But if you consider this charge head, you see this positive are one direction and white part, that is the negative part, is in another direction, which is not in the case at the beginning. Okay. So these dipoles are basically randomly oriented. You can see these dipoles are oriented. If you consider about their this particular charge orientation, one particular side is the positive, another is the negative. So this is called the freezing state. Okay. So this is necessary in order to get the effective piezoelectric. Okay. So this is called the electrical polling steps. So now the question is, you know, why we are the polymer materials are important in these aspects, because so far the commercially available materials are like PZT, BAT, mainly. Okay, but then if you consider about PZT, it is a lead zirconate titanate. Okay, which is toxic in nature because lead is very harmful for human society. So in many countries like European Commission and etc. developed countries, they have already banned lead. So that's why people want another research area, lead-free piezoelectric materials came into the picture. Moreover, it is also brittle in nature because they are ceramics or inorganic materials. So long-term power supply is one of the bottleneck. Okay, because if you apply certain force and it get interrupt or it can break, then it will not work. Okay, so that's why the polymer materials are very much emerging, although the piezoelectric coefficient is relatively less than the inorganic. Inorganic materials, they have a very high piezoelectric coefficient, so their response is very good, for example. But however, in the polymer, they are much, much less. However, the main important with the polymer is they are safe, adaptive, and flexible. So one can make a kind of mat, so large area coverage is possible. And in some cases they are biocompatible in nature, like gelatin, cellulose, etc., PLLA. So they are biocompatible. So it has many application in the biomedical sector, particularly for the implementable biomedical device. So if your tissue is not compatible with the device, then it will create the problem. Okay, so biocompatibility is one of the problem in the case of implantable device. So that can be fulfilled by the polymer materials. Another is the easy fabrication, easy scale fabrication. Because, for example, when I was in Jadavpur University, even with the smaller laboratory, I had the different devices only because of the polymer. I work on the polymer. So that's the one of the, because no high vacuum system is required. Only you have to make a solution and then you have to find out the way to make them as a device. So that's the one of the interesting point. Okay, so many nano generator then came into the picture. For example, self pole PVDF film, because that time actually this corona polling setup, our corona polling setup was not there with us. So make a concept with self pole. That means if we make a PVDF film, then the polling is not required. Another is the ferroelectric ferroelectric nanogenerator. That is nothing but the nanogenerator made with the different types of micropores, okay, or nanopores. So that have a role also. And you see the pore also filled with the nanoparticle. You see the right side image. So that means we have a microscopic dipoles like CH2CF2. And this hole also used as another type that I will discuss later. So it has we can increase several for order of amplitude electric. Another is a plasmonic nanogenerator. So nanogenerator made with the plasmonic component, so it can sense the different type of wavelength. Another the electrospan fiber, so fiber based nanogenerator, that was concept given in 1990 as I discussed. The biopiezoelectric nanogenerator, that also made with the gelatin and different fish component like a swim bladder, scale, fish scale, etc. This is another research area. Now, as a fundamental, it is very important to understand in the case of PVDF why this piezoelectricity coming. Okay, so piezoelectricity, let me tell you, it is coming from the crystalline part. As I told you, the non-femtosymmetric crystals is required. However, in the case of PVDF, it is semi-crystalline. You know, most of the polymer either amorphous or semi-crystalline. Okay, so semi-crystalline means it has a kind of order, but they are not long range. So these small bricks are basically crystalline part, and the rest of the like nodules, they are amorphous. They are not arranged in any good fashion. Okay, so they are like amorphous. So the crystalline part basically give rise the piezoelectricity. However, in the case of PVDF, we have seen there are different crystalline phases. Phases means crystalline polymorph. So one is the alpha phase. So you see the black dot are basically carbon, and this blue are hydrogen, and this is fluorine. So CH2, CF2. Okay. However, they can arrange in different fashions. So this is a dipole, let's say, from F minus to H plus. But see, this is oriented in different directions. So this arrow is downward. Similarly, this arrow is again upward, this is downward. So the net polarization is zero. This is called the alpha phase and transverse phase. So this will not give rise the piezoelectricity. So if one want to increase the, or let's say induce the piezoelectric phase, then one has to reach to this particular state. That is called all transconfiguration, all TT. See, so all dipoles are in the up. You see, all hydrogen are in one direction, wind is another direction. So this is called the beta phase. So once you buy a polymer, make a frame or fiber, etc. But you have to consider whether you have the electroactive phase or not. Electroactive phase means they are responsive to the mechanical stimuli and thermal stimuli. So that is called the beta phase. But there is another phase that is in between phase, intermediate phase. So let's say this is called gamma phase. So these three are trans phase. This gotch, this is like a defect. So this is in opposite direction. So this will get cancelled. However, here you will get some sort of polarization. So this is semi-polar, but this is also showing the piezoelectricity. But in order to get the best piezoelectricity, one has to induce the beta. Okay. So as I discussed the electrospinning process, so you see this is the polymer nozzle and this is the collector, and one has to apply electric field between the tip and collector. And here you can apply the force, I mean through the syringe pump. Then you have a Taylor formation and fiber. So now you can design your collector in different way, like a drum. So if we make the aligned fiber, we can make the higher RPM. Then you have this one, right bottom side, like aligned fiber. Okay. But if you have, if some cases, if you need a random fiber, then either you can reduce the RPM, rotation speed, or we can simply place a metallic collector, like a static collector, fixed. Okay. So in that case also we can collect the random fiber. So these are the ACM image of the random fiber. This is the oriented fiber. And then you see this is the real photographs, this white color one. And if you can imagine it has a very good shape adaptive properties and air permeable in nature. Okay. So the problem with this electrospinning fiber is, you see this image. Okay. So this is a very much spongy, rather air permeable. So if it is air permeable, then if you want to make the electrode, how you will make the device? You have a piezoelectric, let's say nanofiber mat. So you have to make electrode top side and bottom side. So this is a simplistic device structure. So now if you deposit gold, silver, aluminum, or any metal, it will not compatible because this is air permeable, kind of spongy. So what we did, we have shown the all organic approach. So we made an electrospinning process and we try to deposit the fiber which is coated with the conducting materials, conducting organic. Okay. So this is the chemistry part, a very interesting chemistry. We make some strategy so that our fiber is coated with the polymer conducting fibers. This is, I'm not discussing in much detail, but you can get all the detail from here, those are interested. So you can see the PVDF fiber was coated with the P dot PSS, which is conducting in nature. So this white color fiber turn into the black one. Okay, so that means it is composed of the two electrodes, and in the middle we have a piezoelectric. Then we measure IV curve, stress strain curve, and we also show that from the FTI spectroscopy that we have a piezoelectric phase. So this is the characterization technique where we can identify you have a piezoelectric phase. Vibrational bands is the signature of the piezoelectric phase formation. That means another take-home message is that if you do the electrospinning technique, that technique can induce the piezoelectric because of the strain generation. That is interesting. And then we make several devices, measure voltage versus time plot, also power plot with the resistance. So we put a different external resistance. At a particular resistance, we have a maximum power, power transfer theorem, and we can also estimate the how much resistance is important to get the maximum power. Okay. So this way we have measured. This is the same story, but this is made with the compatible biopolymer, that is the gelatin part. But it is very similar story like this one. This is the example that biopolymer one can also use to make them the device. Also, this is another example where we have shown the odd polymers, odd nylon particularly, apart from the PVDF, then gelatin, and then this is odd nylon. Okay, so odd nylons are piezoelectric nature, and through electrospinning technique, what we did here, so electrospinning here, you have to apply positive bias. Okay, and this is the grounding one. You can use it in metallic drum, etc. But if we change to the negative potential, negative, to the needle bias, then you have a different type of surface potential of the fiber. So that is the interesting part we have recently published in APL, that simply by changing the bias in the electrospinning technique, we can rotate the molecule from, you see, this is the oxygen molecule on this side, but here oxygen molecule. So you can change the direction of the polarization. That's what we prove in this work. Then we measure different physiological signal like arterial pulse, facial motion, etc. And we have validated, our BPM to our own sensor with the commercial device. So we can also check that different type of speech signal. If we place our piezoelectric device here, then if we speak like O and PDL, then if we do first Fourier transformation, we can check the frequency domain and amplitude, etc. And different coughing signal. Okay, different type of heartbeat or wrist pulse, like different condition, normal condition, running, smoking, etc. And they give very different type of signal. And then what we do, like we place in different finger, and each finger has different kind of motion. See, so we have shown that the different fingers have a different type of motion, just for the robotic application. This is the example where we have shown the different array of the sensor. And then if we place our hand like this, so you see the pixels are on. Similarly, if we write O, N, P, D, L, then you see we can write down a mapping of the pressure. Okay, so pressure mapping we have shown also. Then this is just to make the long story short. As I told, our piezoelectric materials have a temperature sensing as well. So we have made the electronic skin, but we mimic the skin So we what we do, we have a two modulus, like high modulus and low modulus in the skin, and then we make the electrospinning fiber stacking. In reality, they look like this. You see the stacking cross-section image, and then this is the electrode, top and bottom, and then we can see the temperature and pressure variation. So you see the example. For example, so once you have the temperature, P2 and pyro together, is the baseline is like this. That means the simultaneously piezo and pyroelectric sensing we have been actually demonstrated. Similarly, in different condition, if we place our sensor in the nearby by your nose, then you can also able to track the breathing, because breathing consists of lot of heat modulation, temperature change, and also we can measure different type of gas, etc. So that's our end application. This part I'm not discussing, but then it is very interesting to know, just take home information, since the PVDF or polymers have a very limited piezoelectric coefficient like 35 coulomb per Newton. But if one want to increase it, then what I want us to do, one is to make this kind of cellular structures like coral and then some wood, they have it. So you have to artificially make some sort of cellular structure, means like pore. So what happened? And then if we discharge it to high voltage, then these pore get ionized. Okay, positive and negative separation, charge separation. So these act as a macroscopic type. So once have a PVDF, like this is the macroscopic dipole and this is the microscopic type. Okay, so the charge displacement is possible to make much higher. So use it the 3D printing system to make them electrode structures. Okay, and we have shown that if we charge through the corona polling, high voltage polling, then we can change many things like morphology, contact angle, dielectric property. For example, this is the normal sample, but if we do the 3D structure plane, then contact angle is getting reduced. Similarly, dielectric property, unpoled system, this is the normal one, but then if you pole them, apply the high electric field, the dielectric constant is also changed. Okay. Similarly, in the case of ferroelectricity, what happened? Change the temperature, for example, this group, then what happens? The Riemann polarization basically decreases. But here, Riemann polarization is increases only because of the electrode structure. So this is the down curve. You see, the Riemann polarization is increasing in the case of 3D printed electrode structure. Similarly, in the dielectric constant, in the case of normal, piezoelectric case or ferroelectric materials, at Curie transition temperature, after Curie transition temperature, it declines. So it gets decreased. However, in the case of electrode materials, you see the dielectric constant is increased. So now I will take 5 minutes just to show you some example. So through machine learning techniques, with the help of some collaborator, we have shown that early prediction of the cardiovascular disease is possible to make. Okay, so here we have made some electric sensor, then we do the machine learning technique. So we have shown that once you increase the age, so your different artery has a different, mechanical property, flow rate, blood, etc. get changed. Different physiological parameter like refractive index, augmentation index, they are changing. You see the signal also very much different. Okay, so machine learning technique we try to able to predict. So in the case of like off-base case and normal weight, those is very heavy weight, so they have some deposition right in the artery. So as a result, the response is entirely different from the normal people. Okay. So this kind of sensor we have made. So and then we recently made a screen printing sensor to French group, and with these details I'm not discussing. But then this sensor can able to sense very good sensitivity. It has very good sensitivity towards acoustic signal. Okay, you see the sensitivity, this mark, this sensitivity is very high. As a result, commercial microphone, you see the response, and our acoustics microphone is very similar, and our even giving a much better feature. Okay. So with this, what we did, we have made a acoustic sensor. So different person, you see this person made with, in the France during this visit. So different volunteer, they spoke like I love sun. Then we have recorded the response through our sensor. Then they did engineers people, so they did machine learning, also principal component analysis that I don't understand much, but I can understand that our sensor has the ability to sense them. You see the clustering, so this missile, Devi, so they are belonging to a certain particular regime, right? And through machine learning technique, they can also able to predict very good, like 91% prediction, 98% prediction, etc. Male, female, and this is some, I think, normal and some problem, etc. Voice, different type of parameters they have tested, but the end information is that they try to make the voice print. That means it's a kind of biometric voice biometric they want to do that. So maybe in the next sometime, if I get a scope, then I will discuss about this. This is very interesting because so now we have shown that the possibility to use our sensor as a voice biometric. That means my sensor can able to sense like me and your voice. Okay, because that's the simple thing. Because your voice get modulated. Different people have a different kind of voice, and that is possible to recognize. So that's the way. If we talk with the phone, if I know somebody's voice, then I can able to tell. Okay, you have some problem. You have some health problem, etc. I can able to tell, right? Anybody can tell. Okay, you have something problem. I can see your voice is something different. Like we often discuss like this. Okay. So this is the Professor Shanku's story we know, right? He made a very nice robot, right? And then there is a conversation. So they are like asking, like, তোমার রোবো কি মানুষের মতো অনুভব করতে পারে? So he said, আমি বললাম না, ও জিনিসটা পারে না। আমার বললেন, মানে অ্যানাদার সায়েন্টিস্ট, আর কিছু না হোক, তোমার ব্রেনের সঙ্গে ওর যদি একটা সংযোগ থাকতো তাহলে খুব ভালো। অন্তত তোমার সুখ দুঃখ যদি ও বুঝতে পারতো, তাহলে ওকে দিয়ে তোমার অনেক উপকার। So this is the conversation like 1965 made by Professor, the great filmmaker Satyajit Ray, where he is writing that this kind of robot, if they can sense or they can feel like a human, then many can, impossible things can be done. So this is the area now people are moving towards that direction. That is the emotional sensing. So this is the way, and we have find out some way to impose the emotion to the machine through our sense. Okay, so this is, we are telling that emotional print. So this I will discuss in some platform with you. Then let me tell you. You see the three different signal like arterial pulse, breathing, and voice signals. They are so different. Like happy and angry are entirely different. If you look the kind of pulse. In the case of relaxed, you see this relaxed and sad, relaxed and angry. If you compare, they are entirely different. Breathing is also, you see the rate of breathing in the case of angry is very, very high. Okay. So then if we do the machine learning, then it is even possible to predict the emotional. For example, angry, our sensor can tell very nicely, 100% accuracy. Happy also, sad also, maybe relaxed, he's a bit confused, so some error is there, right? So this is the area people are moving towards that direction. So not only for the biomedical sensing, it is also possible to sense emotion. So we want to tell like emo print. So with this, I would like to conclude my talk, and thank you for your questions. And if you have any questions, comments, and then you can pass to me. At the same time, you can also email me in your future, right? Yeah. So I think I'm done.
Yes, sir. Thank you, sir. And if anybody has any query, please ask, or you can chat in the chat box also. You can put the question in the chat box also. If you have any query, any question, please ask. Sir is there. Anybody has any question? I think, sir, there is no question till now.
Okay, no problem. So this is my email address. Okay. So because
Yes, sir.
I know there are many of faculty, maybe they have a very good engineering
Yes, yes.
engineering background. So they can
Yes,
also collaborate sometimes because I'm collaborating with engineer
definitely,
only
definitely.
for doing the machine learning and other stuffs. Okay. So not only the fabrication part that we can do quite nicely, but then for machine learning part, they can also take part with, you know,
Yes, sir.
kind of interest. Yeah.
Okay, sir. We'll keep in touch with that mail ID and with you also, sir.
Mhm.
And we'll request anybody if they have any queries, they can contact over email also, sir. Okay, na?
Sure, sure.
And before we conclude, I would like to ask all the participants to fill up the assignment as well as the feedback. It is already given in the chat box.
I think I continue too much or I'm in the time.
No, sir. It is perfect, sir. And the presentation is really very nice, sir. Yes, sir.
Okay. Thank you. Then I'm leaving now.
After all, no, sir. We have small token of appreciation for you, sir. We are going to present one small digital memento for you. Kindly accept. We are going to present. Please wait, sir.
Is it visible?
Not yet. Maybe I have to. Okay. Yeah. Very nice.
Yes, sir.
Thank you. Wish you all the best.
Could you please accept, sir, please?
Yeah. So what I
will mail
do?
it also.
Uh-huh.
Kindly accept and we'll mail it to sir.
Okay, fine. Thank you.
Yes, sir.
Thank you.
Thank you, sir, for your well presentation and for the time you have given to us. A nice presentation. We really appreciate, sir. Thank you, sir.
Okay. Maybe you can do little mistake. There was this associate part. You can cancel. Only you can write scientist AF. Okay. Because it is equivalent to
We'll
professor.
rectify, sir. Definitely.
Rest is fine.
Only
Okay.
scientist AF will be there. Okay, na?
Or you can write, but this is then only professor instead of associate one. Yeah.
Okay.
Equivalent to one. Yeah, fine. Thank you.
Thank you, sir. Thank you, sir.
Okay,
Also.
then bye, huh?
Yes, sir.
Now I can leave, right?
Yes, sir.
Okay. Thank you.
Yes, we are going to end and we are going to conclude here. And next tomorrow again, we'll start our program the last day from 11 a.m. as usual. All of you are requested to join again from tomorrow morning. Till then, goodbye. Thank you. Shabak khair. Thank you.